Hey guys, my name is IBM and today I would like to solve Physics 9702 paper 5. This is planning, analysis and evaluation. I'm recording October, November 2022 papers and I'm starting with 5.1 and I will also record 5.2. I'll not record 5.3 because normally 5.3 is the same as 5.1. So without wasting time, I would like to take you to the question paper. So here is the question paper. And I'll first try to the paper is supposed to be 1 hour and 15 minutes. I don't know if I will try to keep time because it is really not easy to draw diagrams on a computer, to draw graphs on the computer, but I'll try my level best. This paper is 30 marks, but is very, very important. So question number 1, a thin copper sheet is suspended from a small hole. So number 1, we need something to suspend this. So what will I use? I may use I could use a wooden rod or a metallic rod through this hole to suspend this. So I'm going to put in a wooden rod through this hole to suspend it. But of course this wooden rod is going to be clamped. So I'll try to clamp this. So this is, I'm just drawing the skeleton of how my setup is going to look like. This is not where I'm supposed to draw the diagram. I'm trying to imagine what I'll include in the diagram. So I'll need a stand and something to hold the sheet, the copper sheet, which is this could be a smooth, thin metal rod. Okay, and is placed in a magnetic field. So I need to create a magnetic field. I'll create a magnetic field. Let me put the magnetic field somewhere. Where should I put the magnetic field? Okay, I'll put the magnetic field somewhere here. So I may put a U-shaped magnet somewhere here. So I'll put a U-shaped magnet somewhere here. Then, of course, the area A and the sheet has area A and thickness T. So T being thickness, I'll use a micrometer screw gauge to measure T. Remember, for such a thickness, I'll repeat and obtain the average. Then A being the area, I'll measure the dimensions or the lengths. And I'll find the area from the length times the breadth. This could be using a ruler. So the sheet is displaced from its equilibrium position through a horizontal distance S naught. So how will I measure S naught? I will need a ruler. So I may clamp the ruler horizontally to help me measure L. So this could be the ruler. So I will put a table here so that my setup is on the table, so the ruler could be supported the other side, so that is perfectly horizontal. This is a support. Okay, then the horizontal distance S of the sheet from its equilibrium position is measured after 5 complete cycles. So It is going to be hard for me to measure S after 5 complete cycles because the sheet might be also continuing to oscillate as I count the number of oscillations, and after 5 I should measure the distance. So the best thing is to use a camera to record this experiment. So I'll use a camera, video camera, so that of course I'll play back frame by frame to be able to measure S. So S will be measured using a video camera where I'll record the experiment with the ruler in position, of course, so that now I view frame by frame to be able to record S. But remember, S naught should be constant. And how will I make S naught to be constant? For S naught to be constant, I need to always ensure that one edge of this is always aligned with I'm going to put a vertical pin somewhere here, a vertical pin aligned with one corner of this. So I'll put a vertical pin. This is a pin aligned with the corner for me to always measure S. Remember, S naught, they say the sheet is displaced from its equilibrium position through a horizontal distance S naught. So to easily measure S naught, I'll need some reference point, which is going to be a pin, P0, which is aligned with the corner of the copper sheet, so that I can always easily measure S0 from that position on the ruler. Because when you displace the copper sheet, it means it's going to be moving through a certain point. Alternatively, I could put a mark on the ruler, then I displace, so that every time I displace the copper sheet from that same point. Also, this pin could help me in counting the number of oscillations. Alternatively, I could put the pin just below the support, so that measurements or oscillations are counted from the center or from the point of suspension. It is suggested that S is related to A by the relationship S is equal to S naught e power negative A B K T. Remember, S is the horizontal distance of the sheet from its equilibrium position after 5 complete oscillations. After 5 complete oscillations. So S is related to the area A by the relationship S is equal to S naught e power minus A B K T. So it's not really very possible for me to it's not going to be very possible for me to change S, but it is easier for me to change the area so that the S automatically changes. So that means S is going to be the dependent variable and A is going to be the independent variable. So having identified the dependent and independent variable, then the experiment is going to be easy. I know how I'm going to measure area by measuring the length using a ruler and calculating the area from length times breadth. Then S, I've said I will use a video camera to measure S. Then there are some constants. B is the magnetic flux density. Remember, the magnetic flux density is measured using the Hall probe. So I'll measure the magnetic flux density using the Hall probe. But remember, every time you use the Hall probe, you measure in one direction, then in the opposite direction, and obtain the average value of V. First direction, then opposite direction, and measure the average value of B. Then K is a constant. Because it has not been defined, then we shall not talk about what instrument we shall use to measure K. So K should be kept constant. Of course, K is going to be a constant. But then the thickness would affect the number of oscillations. So the thickness should be constant, kept constant. The magnetic flux density should also be constant throughout the experiment. Then plan a laboratory experiment to test the relationship between S and A. So we are testing S and A. So we are going to take several measurements. So which graph shall we plot? Let's see. So I will introduce ln because one of the variables is a power of E. So ln of S equals to ln of S naught plus, when I get ln of e power negative a b k t, I only remain with the power negative a b k t, which means, remember, I'm looking at S and A. So remember, A was the independent variable and S was dependent. So we always ensure that whatever is related to the dependent is the subject. So ln of S is going to be equal to negative b k t times A, then plus ln of S naught. If I compare this with y is equal to mx plus c, on the y-axis I will plot ln of S versus, on the x-axis I will plot A. Then that means the gradient is going to be equal to negative bkt, which means that k is going to be equal to the negative of the gradient divided by b times t. So that will be the gradient. That will be k, because they said explain how the results could be used to determine the value of k. So k is going to be equal to that. Of course, the y-intercept is going to be ln of S naught. So we can now think about the procedures, the measurements to be taken. I've mentioned most of them. What to be kept constant? The magnetic flux density should be kept constant, and the thickness, the separation, the thickness of this copper sheet should also be constant because it will affect the number of oscillations. Then analysis of data, I've mentioned which graph should be plotted. Of course, this is going to be a straight line with an intercept of ln of S naught. It should not go through the origin. Safety precautions. For safety, this is a copper sheet which could cause cuts onto your hands. So for safety, I may use gloves to protect hands from cuts on the edges. Alternatively, I'll put a cushion at the bottom here, just in case the copper sheet falls. I could put a cushion, or I could put a sand tray at the bottom here. Okay, so I think that is all. So I think I need to now put this in writing. So in this experiment, A is the independent variable, and S is the dependent variable. So B and T will be kept constant. B was the magnetic flux density, and T will be kept constant. The mistake we all make is to say B and T are the control variables. That is just because to some students do not always follow the instructions, or they don't always attend maybe classes, I don't know. Then of course the measurements to be taken, I'll measure the area. Of course I need to measure the area, so I will use a rule to measure the length. I'm saying length because it is length times the breadth. I will use a ruler to measure the lengths of the sheet to determine the area. To determine the area, A and A is equal to length times breadth or times width, whatever. Okay, then I also have to measure the thickness of this sheet. So I'll use a micrometer screw gauge. I'll also measure. I'll also measure T using a micrometer screw gauge. I'll also measure T using a micrometer screw gauge, but remember I need the average value of T. So this is going to be in different positions. I'll also measure T using a micrometer screw gauge in different positions. In different positions of the sheet and obtain the average value of T. Okay, so I think I have mentioned most of the measurements I would like to take. I think I haven't measured the magnetic flux density of the magnet I'm going to use. So I'll also measure B using a calibrated. I want to measure the magnetic flux density because I'm going to use a horseshoe magnet, which I'm going to show in the diagram. I will measure B using, it must be calibrated, so using a calibrated Hall probe. Whenever the experiment involves magnetic flux density, use the Hall probe, which you studied in paper 4 in magnetic fields and electromagnetic induction. You should use the Hall probe to measure magnetic flux density B. So I'll measure B using a calibrated Hall probe. First in one direction, so use the Hall probe in one direction, then in the opposite direction, and then and obtain the average value of V and obtain the average. So this statement has 2 marks in it. So before I even draw the diagram, I already have, let me check, I have 1 mark, 2, I have 3 marks here. Actually, these could be 2. I have 3, 4 because I'm taking the average of T. I have 5, 6. Before I even plot, because here I'm measuring B using the hollow probe, that's 1 mark. But I'm showing how to make a measurement better. That is, every time I use a hollow probe, I measure first in one direction, then in the opposite direction, and obtain the average. Every time I take a small measurement such as thickness using a micrometer screw gauge for any object. Many times I would prefer to take measurements in different positions of the object and obtain the average value. So I have about 7 marks without even drawing a diagram. Okay. So I will now draw the diagram. So to obtain, to collect, and analyze data. I will set up the experiment. I'll set up the apparatus. Let me just say apparatus as shown above. Okay, so I have to show the diagram here. This diagram is going to be quite complex, but I'm going to try my level best to make it beautiful. So I'll begin by drawing the bench where all my setup is going to be laid. So number two, I'm going to add, I have to start to add a copper sheet somewhere. Let me try to put it somewhere here. So let that be the copper sheet. I hope I've tried my level best. So there should be a hole somewhere here. And I'm going to try and put a support, metallic, it can be a metallic rod. So I'll have to clamp this. But before that, I'm going to add, I think I should add the ruler. I'll make the ruler longer. Then I'm going to put a clamp somewhere here. Sorry, this is a stand. So I'll use the same stand for both the ruler and Okay, so you are going to draw a better diagram, I don't mind, but I'm trying to give you a picture of what I expected, something I expect a student to draw. Okay, so for safety, I'm going to put, at the bottom here, I'm going to put a sand tray. So I'll put a sand tray somewhere here. So I'll call this one sand tray. Of course, remember I'm going to displace this from equilibrium through a horizontal distance S naught, and S naught must remain constant. So I will need a reference point for me to be able to displace this through a distance S naught. So I'll put a pin in line with one end of the ruler. So this is going to be a pin. Because I must measure S naught with a reference point. So I need a pin which is aligned with one edge, so that measurements I can always displace from the same point to until so that I may ensure that S remains constant. S naught remains constant. Then I have to add a magnet. So I have to find ways of adding a magnet here. This is not very easy, but I have to do it. So I'm going to put one pole of the magnet to the other side. And I will put another pole here. I'm going to rub off some of that part so that it looks nice. Okay, if you're better at drawing, you can draw something better, but I just wanted to show some kind of magnet. So let's say this is going to be the south pole, and I will say the other one is the north pole. Okay, so I have to rub off some parts so that the diagram looks really nice. For example, I'll rub off this, and I will have to rub off this so that I draw something to show that the other one is just behind. Okay, so I've tried my level best to add everything that I needed. So this is going to be a horseshoe magnet. This is going to be a ruler. You can call it a meter rule. This is going to be the stand. Then we have a vertical pin somewhere here. We have this is going to be the copper sheet. Then this is going to be a thin. It should be smooth because we need free oscillations. This is going to be a smooth, thin metal rod, which goes through a hole here. There's a hole somewhere here. Okay, so this, remember this was the sand tray. So here I have a bench or the table. So my apparatus is laid on the table. So I think the rest is now very easy. I've finished to draw the diagram. To collect and analyze data, I will set up the apparatus as shown above. So the next thing is going to be to displace the sheet. So I will, sometimes I number my points, sometimes I may not need to number. I can write paragraphs. I will displace, because when the examiner is marking, he reads it as a continuous paragraph. So I will displace the sheet through a horizontal distance. through a horizontal distance S naught, of course measured from the ruler. Remember, S naught should remain constant, or S naught is going to be should be kept constant through a horizontal. S naught is going to remain constant S naught is to be kept constant by initially lining up the corner of the sheet. We have lined up the corner of the sheet with the pin, with the vertical pin. Okay, or you could put a marker. You could put a fiducial marker on the scale so that you always measure S naught from the same position, because we don't want S naught to be different. It should be kept constant. Initially lining up the corner of the sheet with a vertical pin so that S is always the same. So that S naught is always same. So of course now remember I said I'm going to use a camera to record so that I can measure S. So record the experiment using a video camera with the ruler in position. With the ruler in position as shown in the diagram. As shown in the diagram. So record the experiment using a video camera with the ruler in position as shown in the diagram. Then play back. Play back the video recording frame by frame. Frame by frame, or you could do this in slow motion or in slow motion to measure S. Of course, this measurement involving this measurement is quite not very certain, so it means we must repeat this measurement so that we get an average value of S. So I will repeat. Remember, I'm using for the same area which I've already measured. I will repeat the experiment for the same value of A and obtain an average value of S. Okay, so the next thing is now to change A because A was our independent variable. So I will change the area, or I will get a sheet of a different area. So I will repeat the experiment for different values of A until I have say 6 values, until I have 6 sets of values. So I'll repeat the experiment for different values of A until I have 6 sets of values. Now that I have many values, the next thing is analysis, where I will plot a graph. So I will plot a graph of, so we have seen already that we shall plot a graph of ln of S against ln of S against A. And the relationship is going to be valid if the graph is a straight line with the y-intercept equals to ln of S naught. The relationship is valid if the graph is a straight line with the y-intercept equals to ln of S naught. I think the y-intercept was ln of S naught. If there was no y-intercept, we would say the relationship is valid if the graph goes through the origin. But here the relationship is valid if the graph is a straight line with the y-intercept, which is equal to ln of S naught. Then we know that the gradient was equal to negative b k t, which implies that k, which they want us to find, is going to be the negative of the gradient divided by b times t. Then now I think that is the end of the experiment apart from safety precautions. So for safety, I may do the following. Number one, of course this one I've already done it, but I can still write it here. I've placed a sand tray. I've placed a sand tray here so that in case the sheet falls off the road, it just falls into the sand tray. But I can still write it if I'm not very convinced. So I'll say I will place a sand tray, or you could place a cushion below the sheet, just in case the sheet falls. Alternatively, I can write another one. I'll also use gloves to protect the hands. I'll also use gloves to protect hands from cuts. The edges of the copper sheet could be sharp, so they could cause cuts. So it would be better if I use gloves to protect the hands from the cuts. Okay, so I think that is question number one. I've tried my level best to exhaust most of the marking points that the examiner would look for. And maybe just to show you more of the marking points apart from the ones I've mentioned there. So to collect and analyze data that will not give you a mark, I will displace the sheet through a horizontal distance S naught. That will not give you a mark because it's already expected. S naught is going to be kept constant, and this is going to be, you'll be given S naught to be kept constant here, and the examiner may credit you by the second statement for saying initial lining up the corner of the sheet with a vertical pin so that S naught is always the same, or the same mark will be credited on the diagram, the second mark. Recording the experiment using a video camera would give you a mark because it is really very impossible to measure S after five oscillations. And playing back frame by frame or in slow motion to measure S, that would give you an additional mark. I'll repeat the experiment for the same A and obtain an average value of S that will give you a mark, additional mark. Of course, repeating the experiment for different values of A until I have 6 sets of values, that will not give you a mark, but is necessary. Then analysis, which graph to plot, ln of S against A. Analysis when the relationship is valid, if it is a straight line through the origin, then what K would be equal to. Then 1 mark for safety. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And of course, there are almost 2 marks or 3 marks here. So the examiner will pick out only 15 marking points to give you 15 out of 15. Question number 2, which involves plotting a graph. A student investigates a circuit containing resistors and a metal wire as shown in the figure. Resistor Y and Z have resistances Y and Z respectively. The student connects a resistor of resistance R between P and Q. The student then adjusts the length of the wire between the crocodile clips until the voltmeter reads 0. The student measures the length L of the wire between the crocodile clips. The student repeats the experiment with different values of R. It is suggested that L and R are related by this expression, where D is the diameter of the wire and ρ is the resistivity of the metal. A graph is plotted of L against 1 over R. That's where the exam starts from. Determine an expression for the gradient. So I must make sure whatever is plotted on the y-axis should be the subject. So if I make what L the subject, L is going to be, I'm cross multiplying, so it is going to be pi y d squared z divided by 4 times rho, but it is times 1 over r. I made L the subject. If I compare this with y equals to mx plus c, on the y-axis I have L, on the x-axis I have 1 over r. So you will notice that the gradient is going to be pi y d squared z divided by 4 times rho. There is no y-intercept, so c is 0. Values of R and L are given in the table. Each resistance value has a percentage uncertainty of plus or minus 5%. That means the absolute is 5 over 100 times the value of R. And remember, the percentage uncertainty in R is always the same as the percentage uncertainty in 1 over R. If you don't remember, if Y is equal to 1 over R, then absolute in Y is the same as absolute in R over R times the value of Y. So it means the percentage is going to be the same. Each resistance value has that. So they said calculate and record values of 1 over R in the table. We must include the absolute uncertainties in 1 over R. So for the first value, 1 over r, remember there are two significant figures. We maintain the number of significant figures for easy plotting. So since there are two, I'll write two significant figures. So 1 divided by 22. So that is 0.04554545. Remember, it should be two significant figures. There's a power of 10 which has already been mentioned here. It is 0.04545 and so on and so forth. So 1, 2, 3. Because it is power -3, so this is going to be 45. Then I have 1 divided by 27. So this is going to be 37. 1 divided by 33. You can write more significant figures, but plotting. So this is going to be 30. Because remember it is 0.030303 because it is 03 recurring. So it becomes 30 because this is going to be 1, 2, 3, which is 30.3030 and so on and so forth. Then the next is 1 divided by 39. So this is going to be 0.25.6. So it is going to be 26 when you round off, times 10 to the power of -3. Then 1 divided by 47. So this is going to be 21 times 10 to the power of -3. Then 1 divided by 54. This is going to be 19. So I have to add the uncertainties, plus or minus. Okay, so the absolute uncertainty for the first one, it is going to be, of course, the fraction is 5%, so it is going to be 5 over 100 times the value of y, which is 45. I'll ignore the power of 10 because it will be the same. 5 divided by 100 times 45. I'll round off to one significant figure, so this will be plus 2. The next one is 0.5 times 37. So it is 0.05 times 37. So this is going to be plus 2 when I round off. Then we have 0.05 times 30. This is going to be plus 2. The next one is 0.05. I'm saying 5 over 100, then times 26. So this is going to be plus 1. The next is 0.05 times 21. So this is also plus 1. Then 0.05 times 19. So this is also plus 1. So those are going to be the absolute uncertainties. You could write more significant figures, but plotting is easier if the absolute uncertainty is to one significant figure. So plot a graph of L against 1 over R. Include the error bars for 1 over R. Since 1 over R is on the x-axis, it means the error bars are going to be horizontal, like that. Draw the line of best fit and a worst acceptable line. Label both lines. Determine the gradient of the best fit, include the absolute uncertainty. So we're going to find the gradient of the best fit line. We shall find the gradient of the worst fit line, and we shall find the uncertainty by subtracting the two quantities. So I'll first write these values on my paper so that plotting becomes easy. Okay, so now let's plot. The first point is on the x-axis, it is 45. against 71. So 45 against 71. The scale on the vertical axis is each box represents each box represents 5 minus 20, that 25 minus 20, that is 5 divided by 10, 0.5. So each box represents 0.5. So 71 is going to be 2 boxes. So this is the point here. Put a cross, a small cross, and put a small circle. Then next point was 37 against 57.5. 37 on the x-axis, the scale is 20 minus 5, which is minus 15, which is 5 over 10, which is 0.5. So 37, this is 36, 37. Those are 4 boxes. It is against 57.5. 36, 37 is against 57.5. So this is 56, 57.5 is here. The next was 30 against 45. 30 against 45. I think this is direct. The next was 26 against 36.5. So 26 are 2 boxes against 36.5. So 35, 36.5 is here. Then the next one was 21 against 27.5. 21 is 2 boxes. 21 against 27, so this is 26, 27.5, which is here. The last one was 19 against 23. So 15, 16, 17, 18, 19. 19 against 23. So 20, 21, 22, 23 is here. Okay, then I'll plot the error bars immediately. The first one was, the one at the bottom was 1 plus or minus 1. Remember the scale on the horizontal is 5 over 10 small squares, which is 0.5. So plotting 1, those are supposed to be 2 squares. So I have 2 squares to the left and 2 squares to the right. And I draw a horizontal line. I'll increase the thickness slightly so that the error bars look nice. Please use a ruler for the error bars to make them look neat. Then the next one was also 1. The next one from the bottom was also 1. Then the next one from the bottom was 2. So 2, those are going to be 4 small squares. So I'll count to 1, 2, 3, 4. 1, 2, 3, 4. Then the next one was also 2. The rest were 2, 2. So those are 4 small squares. Okay, so the next thing is to draw the line of best fit and line of worst fit. There's only one way I can do this. I'm going to first of all rotate this. And I'm going to ensure that this fits on the same page, because I must balance these points to make the line perfect. I must ensure that the points are balanced. Okay, I've tried my level best to expand the graph, but I'll try to reduce this. So you can draw. I've failed to find a software for rulers and protractors, yet I need them on my tablet. But I will use a manual ruler. So for the line of best fit, you try to balance the points. You must use a pencil so that when you make a mistake, you can easily draw a better line. Because the examiner will check and see if your line cannot be rotated any further. I will not draw the best line, but you should be able to draw the best line. If you notice that there's one point which is far away from the line, then make sure you try and check the line. Like I see the last point is, it is supposed to be 71 against 45, and it was fine. So there is no problem with that. So it's like one of these points is far away from the line. So I'm going to try and eliminate. Wow, this is the worst line I've ever seen. Okay, I'm just going to take this as my line of best fit, even though it could be rotated, but can still be rotated clockwise. Okay, I'll just take this one, but it's not the best line of base. It's not really I really have to check. I'll try another attempt. This is not really a good line. I'm trying to balance the points. Unless I plotted the end of the points wrongly, but it is not really coming out. Let me check the points again. At the bottom I had 19. This is 15, 16, 17. Sorry. Okay, that's 19 against 23, 23. This is 21, 22, 23. The other one was 21 against 27.5, which is correct. This is 25, 26, 27, 27.5. The other one was 26 on the x-axis against 36.5, which is correct. 30 against, it was 30 on the x-axis against 45, which is correct. Then the other one was 35, 37 against 57.5. So it means there's no problem. So I have to try my level best and balance these points. So 1, 2, 3. This is above, this is slightly above. Yeah, I will just take that line, although it could still be rotated slightly. It can still be rotated slightly clockwise. Let me first leave it there so that I draw second one. So which one should I take? Wow, I'm taking that one. You can draw a better line of base fit. So this could be labeled anomalous. Okay, so the next thing I'm going to draw is a line of worst fit. So for the line of worst fit, you can even use a pen because you make a judgment once. There are two ways of drawing the line of worst fit. You either draw from the top of the top error bar to the bottom of the bottom error bar, or you do the reverse. The bottom of the bottom error bar to the top of the bottom error bar. But ensure that in whatever method you choose, all the error bars are being crossed. So if I try to check from the top of the top error bar to the bottom of the bottom error bar, I realize that all the error bars are crossed, so that is a very easy line to draw. I have to change the color to, let me use green. No, the bottom error bar is not crossed, so I have to wrap this. The top of the top error bar to the bottom of the bottom error bar. So I'm aiming at this point here and at this point here. And you see that all the horizontal lines have been crossed. If all the horizontal lines have been crossed, then the line is correct. So the next thing I'm going to also choose the points for the gradient before I rotate the graph again. You can use this, you can draw a single triangle for the gradient, or you could use, if you see you can't find a matching better points, you can just draw two triangles. So I'm looking for corresponding points where I can use a single triangle for the line of, for the gradient. There is this point here, and I could take this and this on the y-axis. On that axis, then I could take at the bottom, I could take this point and this point here. Okay, so for the triangle, make sure you draw a very neat triangle. I'll try to increase the thickness. So I'll put a ruler so that I draw a very neat triangle for the gradient. So that is going to be my triangle. Okay, so I will rotate, let me rotate back the graph so that the points are visible and big enough. Of course, when I rotate back, it is going to be kind of different because it is going to be over magnified, but it's fine. Okay, so we have to label our graphs because they tell us to label. So this is going to be the line of best fit. And this is going to be the worst fit line. So I have to find a gradient, so I'll write out the points that I will need to use. I'll just read them at once. I'll just write them on paper so that I transfer them at once. So for x2, for the best fit, I'll read them from the graph. I will just first write them on paper. So for the best fit, what is going to be like my y2 is going to be this point here, which is 70.5. And for the worst fit, what is like my y2 is going to be this point here, which is 65.5. Then that is y2. x2 is the same for both. So we have this point here, it is going to be the value for x2 for both, which is 41, 42, 43.5. So x2 is 43.5 for both lines. Then we come here for x1 for green is this one for worst fit, which is 15, 16, 17, 18. So it will be 43 minus 18. Then for the blue one, oh, sorry. So this is where the graph touches the line. Sorry, it's not 18. It is actually this one here, this point here for green and 20 for blue. So for 20 it is 20. For blue it is 20, then the other one is 19.5. For green it is 19.5. For blue it is 20. Okay, so those are the points for the graph. Then on the y-axis, y1 is the same. It is the same point here, which is 25.5. So when you do the experiment, when you draw the graph, you may not get exactly the same values, but these are just guiding values. So the gradient of best fit is going to be, we saw it was 70.5 minus 25.5 divided by 43.5 minus 20. For the worst fit, it was 65.5 minus 25.5 divided by 43.5 minus 19.5. So I'll press my calculator. 70.5 minus 25.5 divided by 43.5 minus 20. Remember, the x-axis was multiplied by 10 to the power of minus 3. So I should not forget that, times 10 to the power of minus 3 times 10 to the power of minus 3. So that is the answer, divided by 1 exponent minus 3. So this is giving us a 1.91 times 10 to the power of 3. Then the other one is 65.5 minus 25.5 divided by 43.5 minus 19.5. So I'll just multiply this times 1 exponent 3. So this is going to be 1.67. This is equal to 1.67 times 10 to the power of 3. Then the uncertainty is going to be the difference. So it is going to be 1.91 minus 1.67 times 10 to the power of 3. This is the uncertainty. So 1.91 minus 1.67. So this is 0.24 times 10 to the power of 3. So the gradient can be written as 1.91 plus or minus 0.24 times 10 to the power of 3. Okay. Then a student measures the diameter of the wire. The student's values are shown here. Determine the average diameter D, include the absolute uncertainty. So the average we shall just add and divide by their number. So it is 0.263 plus 0.262 plus 0.263 plus 0.257 plus 0.262 plus 0.259 divide by 1, 2, 3, 4, 5, 6. So divide by 6 and I'm getting 0.261. So the average is 0.261 plus or minus the uncertainty, of course, the absolute uncertainty in D is going to be half of the range. The range is the highest, which is 0.263 minus the lowest, which is, I think, this one, 0.257, then divide this by 2. So 0.263 minus 0.257 divided by 2. So that is 0.003. So this is 0.003. Resistors Y and Z each have a resistance of 22 ohms plus or minus 5%. Use your answer to A, C, Roman 3, and D. Determine the value of rho, include an appropriate unit. Of course, remember rho was, I think rho was density. I mean, it was resistivity. So even without calculation, without finding the units, you can predict that it could be ohm meters, but it will depend. Let's first find rho. Remember the gradient from the first part of the question. What was the gradient? The gradient was pi y squared y d squared z over 4 rho. So I can make rho the subject in that expression. So making rho the subject, I think rho is going to be pi y z d squared divided by 4 times the gradient. Okay, so I'm now going to substitute. So this is pi times y and z are 22, so it will be 22 times 22. The diameter here is in millimeters. So because the gradient is going to be in centimeters per ohm, I'll change D. Okay, I'll leave D in millimeters. There's no problem with that. So this is going to be 0.261, that is squared, divided by 4 times the gradient. The gradient was, what is the gradient? I think it was 1.91 times 10 to the power of 3. Okay, let me first press the calculator here. Let me first find the unit so that the gradient on the vertical we had centimeters, on the horizontal we had per ohm. So the gradient was centimeters, ohm centimeters, yet the numerator is millimeters squared. The numerator is ohms times millimeters squared. So I'll change the gradient here. I'll change it from centimeters ohms to another unit here, from centimeters ohms to millimeters. What will this be? 1.91 times 10 to the power of 3 centimeters per ohm. I mean over centimeters ohms. I want to change this from centimeters to millimeters so that okay, let me first change this. So I'll say times. I want to change this to SI units. So I'll simply set times 10 to the power of minus 3 to change this to meters. And I'll also change the gradient to times 10 to the power of minus 2. This is the gradient. So that now this is in meters squared, and this is going to be in meters ohms. Okay. So let me just press my calculator. So this is going to be pi times 22 squared times open brackets 0.261 exponent minus 3, but this is squared, divide by 4 times open brackets 1.91 exponent 3 times exponent minus 2, it becomes exponent 1. So it means this is going to be 4.95 times 10 to the power of minus 4. 4.95 times 10 to the power of minus 4. The units we have ohms times meters squared divided by ohms meters times ohms. So this cancels with that. So I remain with ohm meters. I multiply this to change this from centimeter ohms, that was the gradient, to meters ohms. I multiply this by minus 3 to change from millimeters to meters. So I think that is going to be fine. This was just for the sake. Then determine the percentage uncertainty in the gradient. Of course, there I don't need to change anything. So percentage uncertainty in rho. We just look for those quantities with uncertainties. Pi and 4, we shall ignore them. We have dyz, so it will be percentage in y plus percentage in z plus twice. Percentage in d, because this is squared, plus percentage in the gradient. So this will be 5 plus 5 plus 2 times percentage in d. Percentage in d is going to be 0.003 over 0.261 times 100 to make it percentage. Then plus percentage in the gradient. Remember the gradient was had an uncertainty of 0.24 and it was 1.91. So I'll say this is 0.24 over 1.91, then this is times 100 to make it percentage. So I'll start with the fractions. So 0.003 times 2 divided by 0.261 times 100, that is approximately 2.2%. So you have 5 plus 5 plus 2.2 plus greater than 0.24 times 100 divided by 1.91, which is 12. This is 12, or approximately 13. So I have 13 plus 10 plus 2.2, approximately 25%. So the answer here is going to be about 25%. Then determine the resistance R that would give a value of L. Oh, by the way, if you're very poor at finding uncertainties, you can find this rho for the best fit. We already have it up there. You find rho for the worst fit using the worst fit values. That means you put the worst gradient. Then you find the absolute in rho by subtracting rho, maybe rho worst fit minus rho best fit, or the other way around. After it is plus or minus. Then you can now find the percentage in rho as being the absolute in rho divided by rho times 100. This could also give you this, not the same answer, but it will be an acceptable method. You get rho for the absolute, we have it above. You repeat the same substitution, but this time you put the worst gradient, you get the second value. Then you subtract to get the absolute, then you change it to percentage. When you have the resistance R, that would give a value of L of 95.0 degrees, 0.0 centimeters, include the absolute uncertainty. So remember L was equal to, I think it was pi y d squared over 4 rho times z times 1 over r. There was a z somewhere here. Okay, and remember this was the gradient, and I want to find r. So if I make r the subject, so L is equal to the gradient over r. So I want to make r the subject. I will simply say that r will be the gradient divided by L. So I'll just substitute this for simplicity. So R is going to be the gradient. Remember the gradient, they want the answer in ohms. So I'm going to change the gradient. Anyway, the gradient is 1.91 times 10 to the power of 3. Remember this was centimeters ohms. Divide by L, which L is given as 95.0. This is centimeters, so centimeters cancels. So 1.91 exponent 3 divided by 95. So this is giving us 20.1. As simple as that. So that marks the end of this paper. Of course, some failures think it is very easy to do this on a computer, on my HP pad. If you think it is easy, the YouTube is open. You can also do it. Until next time, for those who love me, bye bye.